Some takeaways from that first video was that if you have your alkene and you have water and you just try to react them together, nothing happens. In order to get this alkene to react with water, you have to have a catalyst, and the catalyst that we're going to use is hydronium. So just to kind of put it out there, this mechanism is really no different than the alkenes reacting with HBr. And once you can take a broad view, you see that even though the tiny little details are changing, the overarching roles really aren't changing too terribly much. So just like before with alkenes with HBr, the first step was the alkene acting as a base, and then our acid acting as an acid. The same thing is going to go here. So this alkene, the alkene is going to have some electrons in the double bond. They're going to act as a base and pull off a hydrogen or abstract a hydrogen from the hydronium. If we make a bond, we have to break a bond. So we're going to break that bond right there and have electrons go to the oxygen. And so we can draw our next charged intermediate from this reaction. So we're going to get our alkene that's been reborn as a carbocation. And now let's go ahead and I'm going to change this hydrogen to being red, just so we can kind of keep track of him. So now if this is your red hydrogen that got attached, that red hydrogen got attached to this molecule right there. So the red hydrogen adds to the end, and according to Markov-Nikov, we get carbocation in the middle, where it has the most substituents. And so at this point, what we're going to do is we've really made a very nice electrophile. So we have a very nice electrophile, and I'm just going to abbreviate it as E+. So now we can think about our nucleophile. And so the nucleophile in solution, it used to be a Br-. And what's really changing in this case is we're still going to have a nucleophile, but it's no longer going to be Br-. In this case, our nucleophile is going to act as water. So water was the other partner in this reaction. So we have water, your alkene, and your catalyst. And so in this case, this is going to be the action of the water. This is actually acting as our nucleophile. And so this is very important to point out that, remember, we talked about nucleophiles as either having a negative or a neutral charge. So just the fact that this water is neutral doesn't keep it from acting as a nucleophile. It can still act as a nucleophile. Nucleophiles do the attacking. And to do an attack, you have to have electrons to do an attack. The electrons have to come from someplace, and they're going to come from the oxygen. So the electrons are going to start right here, and so this is your electron source. And so even though this is the electrophilic molecule, we can be even more specific, talk about an electrophilic position. And the electrophilic position is that carbon with a positive charge. So we have our start location, which is right here, and we have our end location, which is right there. So start and end. And so start and end, we're making a new bond between that oxygen and that carbon. So if this was carbon 1, 2, and 3, we had our oxygen attaching to carbon 2. Let's go ahead and color everything in. So after we attach this oxygen to the carbon, a very common mistake is for students just to say, well, okay, this is the end. And this is actually not correct. So this is no-go. This is a sad face, no-go. The reason this is a not good thing to draw is really if you say that you have already gotten to your alcohol, you're really skipping, again, the details of bond making and bond breaking. So if you think about this arrow, all the arrow is really saying is that the oxygen is making a new bond to carbon 2. We haven't really said anything about this blue oxygen, breaking off from a green hydrogen, or the blue oxygen breaking off from its purple hydrogen. So because we haven't drawn arrows, we have to draw, both of those hydrogens still being there. And so at this point, we still have both the green and the purple. So we have our green and we have our purple. Both of these hydrogens are still there. And if we think about charge calculation, so this oxygen was neutral at the beginning, and at the end of the day, it used one of its lone pairs to make a new bond. And so if these lone pairs, these blue lone pairs, were used to make the bond, this is the location for those blue electrons right there. And I guess really in this case, these would be the white kind of electrons, just kind of hanging out. So overall, in the middle, we had a positive charge. And so that means that right over here, we have to have a positive charge as well. So can you spot where I've gone wrong with this molecule? I'll give you a second to think about it. So hopefully you saw that this blue oxygen, now if you did a formal charge calculation, this guy's actually positive. So it's going to be 6 minus 1, 2, 3, 4, 5. And so it's 6 minus 1, 2, 3 bonds, and then 4, and then 5 for the lone pair. And so now 6 minus 5 is positive 1. So this guy's going to be positive. So this is actually, this mechanism is more complicated than what we've done before, because with the HBr reaction, it was just like the two-stepper, three-arrow mechanism. So we're actually really, really close. If you compare and contrast this molecule up above to this molecule down low, we're like 99% of the way there. We just have to complete the mechanism. So what we're going to do is we have, plenty of water in solution for this step. We have plenty of water. So we can have water act as a base, and it can actually do a really good job of abstracting either this purple or the green hydrogen. It really doesn't matter which one that we choose. We could really choose either one to leave, and it doesn't really matter so much. But after we abstract either the purple or the green hydrogen, we'll get this kind of molecule with OH, and voila, we've actually gotten to the end product pretty easily. So all that really had to happen was one extra step. And even though it's one extra step, this is a very important step to show, because without this step, it's not really obvious how we lost a hydrogen. And it's going to be really important in a moment, because we're going to try to, in the next video, we're going to make not an alcohol, we're going to be making ethers. And it's really confusing about how we make the ether unless you really understand this step right here. So it's absolutely important to really understand this part.